Hey everybody, we're live in stereo, so we're just continuing with the MCQs of the 2024 set, and without further ado, let's just hop into the MCQ. It says element Y and Z are both in period 3 of the periodic table. Now, period 3, you need the periodic table to be right in front of you at all times. So this is my annotated periodic table, which we have annotated since the start of this chemistry course, right? So it's saying it's in period 3. This is my period 3, so it can be sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. It can be either or, right? Now it says when chloride of element Y is added to water, it reacts and gives you a solution of pH 2. And this is so important to understand because you know that which chlorides give you a pH of 2. If you look at your period 3, you have sodium chloride, you have magnesium chloride, you have aluminum chloride, you have like what else you have, silicon, phosphorus, sulfur, chlorine is already, so silicon chloride, phosphorus chloride, PCl5, and yeah, sulfur and chlorine and argon does not form any chlorides. This in itself is chlorine, and sulfur for our course does not form any chlorides, right? Now we know when we add these three, effectively aluminum chloride gives me around a pH of 2, and which gives a pH of 3, and these two give me about a pH of 2, right? And if I add them to water, why does it give me a pH of 2? Why? Because when you add SiCl4 to H2O, it forms SiO2 plus HCl, right? And we already know all of these equations. PCl5 added to water, it gives you what? Phosphoric acid, H3PO4 plus HCl. That's it. So these two will give you, if the element is silicon or phosphorus, it'll give you a pH of 2. So it can either be silicon or phosphorus chloride, right? Now I think when element Z is added to water, it dissolves and gives you a pH of 7. Now if it gives you a pH of 7, which chloride gives you a pH of 7? You might think it's magnesium chloride, which you are absolutely wrong. Magnesium chloride gives you a pH of 6.5 because magnesium is smaller, it has a charge of 2 plus, and therefore it can extract some of the hydrogen ions and give you an acidic solution, right? A slightly acidic solution. NaCl is absolutely neutral. So in fact, it's NaCl. When you add it to water, it does not hydrolyze in water, it does not react with water, it just dissolves, right? So it gives you sodium ions and chloride ions as it is, right? So that's what happens. So element Z must be sodium, and element Y can either be silicon or it can be phosphorus. That's it. That's all. I think which statement explains these observations? Both chlorides hydrolyze in water. It's absolutely incorrect. I just stated sodium chloride does not hydrolyze in water. Neither does magnesium chloride, because they just dissolve. We've studied them. They don't react with water. They just dissolve to give you MgCl2, aqueous, NaCl, aqueous. So they don't both hydrolyze in water. Hydrolyze means they react, right? They don't. Now, and yes, silicon chloride and phosphorus chloride will react. That's true. Element Y is magnesium and element Z is sodium. Y can't be magnesium because magnesium gives you a magnesium chloride when dissolved in water gives a pH of 6.5. So B is wrong. Element Y is phosphorus and Z is aluminum. Z can't be aluminum because aluminum gives you about a pH of 3. You all know this, right? If you take aluminum chloride and add it to water, it forms what? Aluminum H2O6 3 plus gives you Al. It extracts a hydrogen ion, so it's AlH2O5OH, and then the charge is 2 plus now because a hydrogen ion is extracted, right? And this hydrogen ion can react with the chloride ion in the solution to give you HCl. But that's that. So C is also wrong. Element Y is silicon and Z is sodium. Yes, Y could have been silicon or phosphorus. Both would have been correct. So it is silicon and Z is absolutely sodium. So you could have solved this question very quickly by just understanding that pH 7 is because of sodium, and therefore D would have been the correct option. I just wanted to go over all the options, right? Now, question number 2 says, aluminum, silicon, and phosphorus are elements in period 3 of the periodic table. Each element forms an oxide. Which row is correct? Now, aluminum oxide. Aluminum oxide, is it basic? Absolutely incorrect. It's amphoteric. Aluminum oxide is an amphoteric oxide. It can act as a base when reacted with an acid, and it can act as an acid when reacted with a base, right? To give you salt and water, obviously. Is giant ionic? Absolutely. It's an ionic compound. Aluminum has a charge of 3 plus, O is 2 minus, and you have 2 aluminum for 3 O2 minuses, and this is in fact a giant ionic lattice. Absolutely. So B can be true. It says it has high melting point. Absolutely, it does have a high melting point because it's an ionic compound, right? Ionic bonds are pretty strong. It has strong electrostatic force of attraction. Vigorous reaction with water. Sir, just sorry to bust your bubble. Aluminum oxide is insoluble in water. It does not react with water. Yes, it does react with bases and acids, but it's insoluble in water effectively, right? So we have to select between B and C now. Now if you look at silicon oxide, silicon dioxide, or silicon 4 oxide, it is in fact having a high melting point, but it's not giant ionic. Therefore B is wrong and C should be the correct option. This is a giant molecular lattice, a giant covalent lattice, or a giant molecular lattice. That's it, or giant molecular structure. So C is the correct option. And you could have even looked at this P4O10. It is simple molecular, but the problem was in this statement right here. Silicon 4 oxide is not giant ionic, and P4O10 absolutely has a low melting point. It's a simple molecular structure. Done. Next, which statement is correct? The atomic radii, question 18. Okay, so hold up. Okay, so it says which statement is correct? The atomic radii, or the atomic radius of silicon, is larger than that of aluminum. Again, I have to have the periodic table by my side at all times to know all of this good stuff, right? So he's saying that the atomic radii of silicon is larger than aluminum, and that's absolutely BS, because you know that across the period, the atomic radii decreases. Why? For the same reasons. The nuclear charge increases, the shielding effect almost remains constant, and so the pull on the outermost electron increases, the effective nuclear charge increases, and therefore the nuclear attraction for the outermost electron increases, pulling in the outermost electron and making the size smaller. So silicon is not larger than aluminum, it's across the period, so silicon is smaller than aluminum, right? So silicon is not larger, it's smaller. So this is incorrect statement, sir. The boiling point of chlorine is higher than that of silicon. Now silicon is a giant molecular lattice, or a giant molecular structure. It's giant molecular. Silicon or silicon 4 oxide, both are giant molecular, please. So chlorine absolutely is a simple molecular structure. It does not have a higher melting point than silicon. It would have ruined the entire graph for melting points that you've seen up until now, right? It looks something like this. This is where silicon lies at the top. It's the king of melting points, or boiling points, right? So B is absolutely incorrect. The first ionization energy of sulfur is greater than that of phosphorus. Again, you know that sulfur and phosphorus, that's where the exception lies. Phosphorus is 3p3 and sulfur is 3p4. Now, although ionization energy, what happens to the ionization energy across the period? Across the period, the ionization energy increases, and we know the reasoning for it is the same. It's this particular reasoning. Nuclear charge increases, shielding is almost constant, the effective nuclear charge increases, the net nuclear attraction for the outermost electron increases, and therefore the ionization energy increases. It's difficult to remove the electron across the period, right? But if you look at phosphorus and sulfur, just like magnesium and aluminum are an exception, phosphorus and sulfur are also an exception, right? What's that exception? Well, phosphorus is P3 and sulfur is P4. Now, although the ionization energy increases across the period between phosphorus and sulfur, you realize that phosphorus actually has a higher ionization energy. Phosphorus has a higher ionization energy than sulfur. Why? Because of spin pair repulsion. So phosphorus in fact has a higher ionization energy, and you have to, if this were to come in theory, it comes for usually 2 marks, because you have to tell the examiner that although sulfur has a higher nuclear charge, it is outweighed by the impact of spin pair repulsion, and that is the reason why spin pair repulsion outweighs the effect of this higher nuclear charge, because understand that sulfur has 16 protons, therefore the nuclear charge is plus 16, and phosphorus has 15 protons, the nuclear charge is plus 15. So although although sulfur has a higher nuclear charge, the spin pair repulsion for sulfur due to this one fully filled orbital actually outweighs this higher nuclear charge, and therefore phosphorus has a higher ionization energy than sulfur, right? So if you were to go across the period, we know that we don't see this trend. What we see is sodium to magnesium, the ionization energy increases. Then from magnesium to aluminum, it decreases. And we know why, because of that additional shielding. Then increase from aluminum to silicon, phosphorus. It increases from aluminum to silicon, then silicon to phosphorus. And then between phosphorus and sulfur, there is a dip. Ionization energy decreases because of this pair repulsion. And then again, ionization energy increases and increases. So this is the graph that you see for ionization energy, right? So the first ionization energy of sulfur is less than that of phosphorus. Why? Because of spin pair repulsion, which is experienced or observed in phosphorus, right? In sulfur. Although sulfur has a higher nuclear charge, the spin pair repulsion for it actually results in a lower first ionization energy compared to phosphorus. Now, D says the electrical conductivity of magnesium is greater than sodium, and that is absolutely correct, because magnesium contributes 2 electrons to the C of D localized electrons, whereas sodium contributes 1 electron to the C of D localized electrons. So magnesium has more delocalized electrons, and more delocalized electrons, which are, you tell the examiner, more localized electrons which are free to move, right? Per magnesium atom, it contributes 2 electrons, whereas per sodium atom, it only contributes 1 electron to the delocalized electrons. And the more electrons you have, the higher the electrical conductivity, because you have more electrons which are free to move, right? And similarly, the more electrons you have in the delocalized structure, the higher the melting point as well. That's the reason why, if you look at the electrical conductivity between sodium, magnesium, and aluminum, the electrical sodium, this is magnesium, this is, let's suppose, aluminum. So the electrical conductivity between sodium, magnesium, and aluminum increases, and so does the melting point, right? So sodium, magnesium, aluminum, both have to do with the same idea of more delocalized electrons. Done? 24. All solubility data in this question is given at the same temperature. The table gives some data for compounds of calcium and for compounds of X, and identified an unidentified element of group 2. So X is in group 2. Okay. Again, periodic table should be by your side. X is in group 2. So I've identified that X must be somewhere here, right? Now, the question is pretty simple. He's saying that what is the missing data for element X? And he's given you data for calcium. He's given you the decomposition temperature of the carbonate. Now you know what happens to the stability of carbonates, the thermal stability. If this is calcium carbonate, and let's suppose at the top you have magnesium carbonate, and you have, like, as you go down the group, you have strontium carbonate, barium carbonate. What happens to the stability? Strontium carbonate, barium carbonate. The thermal stability actually increases. Thermal stability actually increases, right, down the group. So if the thermal stability increases down the group, you know that more energy is required. It's more stable, so more energy, more heat, more thermal energy is required to decompose this fella, right? So you understand that if calcium carbonate is 840, should X carbonate, if it has a higher decomposition temperature, should it be at the bottom of the group or at the top? It should be at the bottom, because the thermal stability increases as you go down the group, so more energy is required to decompose it, sir. So you realize that calcium carbonate, if this is calcium carbonate, X can be something lower than this. X can be strontium, it can be barium, and so on and so forth, right? Now you think the solubility of sulfate is 4.66 into 10 raised power minus 3. Now please understand that as you go down the group, now we know that X is somewhere down, right? And we know that as we go down the group, the solubility of sulfate decreases. Sulfates become more insoluble. That's the reason why barium sulfate gives you a white PPT. That's why you use barium sulfate for your test, and you've been using it since O levels and IGCSE, because barium sulfate is highly insoluble. So what happens to the solubility of sulfate as you go down the group? We know that X must be somewhere here, so the solubility of sulfate should decrease, right? It should be It should decrease, right? And decrease, by decrease we mean it should be more soluble or less soluble. It should be less soluble, right? So these two should be the correct options. C and D are automatically wrong, because you understand that solubility decreases, right? It is less soluble. See, this was, let's suppose, erase the 10 raised to the power minus 3 from it, right? Erase the 10 raised to the power minus 3 from it. Just multiply it with 1 million. If you get confused in these minuses, multiply this with 1 million and multiply this with 1 million. You will see that this is a higher number compared to this. This is a higher number compared to this, right? So solubility, in fact, should decrease. If ever you get confused in these minuses, just multiply it with a million in your calculators. You will notice that this will be 466 and this will be 71.1. So is 466 greater or 71.1? 466 is definitely greater, so it's more soluble, and that's the reason why this is correct. So these are all the tricks and tips that I could give you guys in the MCQs to quickly solve it. Similarly, solubility of hydroxides. We know that the solubility of hydroxides increases down the group. So hydroxides, barium hydroxide is the most soluble. Just like barium sulfate is the most insoluble, barium hydroxide is the most soluble. So should you have a value greater than this or less than this? Obviously a value greater than this. And which value is greater than this? This is minus 5. This is lesser. This is minus 5. So therefore B is the correct answer. B is minus 3. 3.37 into 10 is power minus 3. And this is 1.53 into 10 is power minus 3. So this is a greater value. And if ever you get confused, just multiply this with 1,000. When you multiply this with 1,000, you get 1.53. Multiply this with 1,000, you get 3.37. So which one is greater? So 3.37 is greater, which means this is more soluble, right? So that's the idea. Question 25 says, question Schwachken, 25 Schwachken. It says a solid sodium halide, NaX, okay, it can be NaCl, NaBr, whatever, is saying it reacts with concentrated sulfuric acid, and the lowest oxidation state of sulfur in the products is +4, which means it's SO2. It gives you SO2 as the lowest oxidation state, and NX must be sodium bromide then, because if it was sodium iodide, if it was sodium iodide, it can give you SO2, it can give you S, it can give you H2S even, in which sulfur is -2, here it's +0, and here it's +4. So you're saying the lowest possible that it gives you is +4, therefore it's the sodium bromide halide that you have, right? And if it was, you might think, why is it not sodium chloride? Because sodium chloride does not reduce sulfur, right? Concentrated sulfuric acid, the sulfur in concentrated sulfuric acid. Or you could say concentrated sulfuric acid cannot oxidize sodium halide, sodium chloride, right? So he's saying halogen Y2 is less volatile. So automatically C and D are incorrect. We have to select between A and B. And he now is saying that halogen Y2 is less volatile. Less volatile means that it must be a liquid or a solid. If halogen X2 is a gas, then this must be liquid or solid, right? Less volatility means that stuff. Less volatile as you go down the group 17s. Down group 17, chlorine is a gas, then bromine becomes a liquid, then iodine is a solid, astatine is a solid, right? Fluorine is a gas. So less volatile. Volatility, what happens to the volatility as you go down group 17? Volatility, what happens? Decreases. You can no longer escape easily into the air. Volatility is the ability of particles to escape into the air. And if it's a solid, it cannot easily escape into the air because of strong intermolecular forces of attraction. So you'll realize that he's saying Y2 is less volatile than X2. What is Y2? So X2 is basically Br2, right here. X2 is Br2, right? Bromine. Right here. So what should be Y2? Y2 should be iodine or something lower than that. So B is the correct option. Why is B the correct option? Again, because bromine is more volatile. This X2 is more volatile than Y2. Or you could say Y2 is less volatile than X2. Right? Same idea. Next question. Compound Q dissolves in water to give you Q aqueous, does not react with dilute sulfuric acid. Okay, saying it does not react with dilute sulfuric acid. I don't care. Okay, good stuff. Now he's saying Q aqueous forms a precipitate when aqueous silver nitrate is added. This precipitate is partially soluble in aqueous ammonia. Okay, this is an interesting question. Very interesting question. See, understand that if I have compound Q and these are my options. Now he's saying that it dissolves in water. So barium bromide start to dissolve these stuff. Barium iodide and magnesium bromide and magnesium iodide. The way I like to solve such questions is to dissolve them, which is to make them into ions. So Br minus, these are my ions, Ba2 plus and Br minus. Similarly here my ions are Ba2 plus, and when you are good at it you don't even have to do this stuff, but the way I like to explain it is through these containers, right? So I have these negative ions in these 4 containers, right? They're all aqueous. See, he's saying it dissolves in water. All are going to be aqueous, all. Now he's saying he adds dilute sulfuric acid to it. So sulfuric acid is what? H2SO4. It's the H plus ion and the sulfate 2 minus ion. So H plus sulfate 2 minus, 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 and he's saying it does not react. What that means is it does not show any results, no results. And you know, if you have sulfuric acid right here, the barium ion and the sulfate ion are going to make a precipitate. The barium ion and the sulfate ion are going to make a precipitate, and he's saying there's no reaction, so it cannot be the barium ion, because if it were the barium ion you'd see a precipitate forming, you'd see a BaSO4 white PPT forming, but you aren't. So barium bromide or barium iodide, both are incorrect just because it contains that barium 2 plus ion, and it is saying it does not react with sulfuric acid. And yes, magnesium doesn't. Why? Because magnesium 2 plus and SO4 2 minus are soluble, so you don't see anything. Magnesium 2 plus, SO4 2 minus, H plus, Br minus, they're all soluble, so no precipitate forms, right? You know, as you go down the group, the solubility of sulfates decreases. So at the top it's pretty soluble, magnesium sulfate pretty soluble, that's why you see no reaction. So A and B are wrong. I think Q aqueous forms a precipitate when aqueous silver nitrate is added. This precipitate is partially soluble, so it can't be iodide, because you know that for the iodide ion it must be insoluble in both cases, in concentrated aqueous ammonia and even in your dilute aqueous ammonia. And if it's the bromide ion, it's soluble in dilute ammonia and it's insoluble it's insoluble in dilute ammonia. What am I saying? It's insoluble in dilute aqueous ammonia and it's soluble right here. And if it's chloride, it's soluble in both cases. So we know this, right? This is dilute aqueous ammonia and this is conc aqueous ammonia. Done. So it's partially soluble, which means it must be bromide and not iodide. Done. Next question. Pretty basic questions, huh? Nitrogen dioxide is a gas that contributes to air pollution. It is produced in the internal combustion engines because there's high temperature, provides it with the activation energy and whatnot. Which statement is correct? Nitrogen dioxide acts as a catalyst. Absolutely does. Be it nitrogen monoxide or dioxide, both are catalysts. In the atmospheric oxidation of sulfur dioxide to sulfur trioxide, absolutely correct statement, right? That is absolutely correct. You know, you take NO, reacts with half oxygen to give you NO2, and this NO2 reacts with SO2 to give you SO3 and NO. Now you might be thinking, sir, isn't NO the catalyst? It is. It's being used up and then it's being made. So catalyst is a chemical substance which is not used up. It takes part in the reaction, but as soon as it's used up, it's also being made. But what about NO2? NO2 is not being made. No, NO2 is being made because as soon as this NO2 is being used up right here with the SO2, more NO2 forms because it's a reversible reaction. So more NO2 forms, the equilibrium shifts to the right, makes more of it. So as soon as it is used up, more of it is formed. So NO2 and NO both are my catalysts. We need to understand that in the atmospheric oxidation of sulfur dioxide to sulfur trioxide, after which acid rain happens, right? Now, nitrogen dioxide reacts to form nitrogen monoxide in the catalytic converter. No, catalytic converter mein nitrogen monoxide and dioxide don't form. Nitrogen dioxide goes into what? It goes into nitrogen. Even if it's nitrogen monoxide or dioxide, both go into nitrogen. That's the whole purpose of these very expensive catalytic converters. Now, I think PAN forms when nitrogen dioxide reacts with gases formed by the complete combustion of fuel. No. NOx reacts with volatile organic compounds which are usually unburnt hydrocarbons. So NOx reacts with unburnt hydrocarbons to give you PAN, which further reacts with ozone and a lot of other chemicals to give you smog. So this is how it goes. Complete combustion of that fuel would not give you volatile organic compounds. It wouldn't give you unburnt hydrocarbons. So C is wrong. Under high pressure in the internal combustion engine, nitrogen dioxide forms from the impurities of the fuel. Absolutely incorrect. Nitrogen dioxide does not form from the impurities of the fuel. Fuel normally does not have nitrogen in it. It forms because of the nitrogen in the air reacts with the oxygen in the air. At high temperatures, it forms nitrogen oxides, NOxes, right? So it does not form from impurities, rather it's because of the nitrogen in the air which reacts with oxygen, and the internal combustion engine provides it that high temperature as the activation energy. 28. Nitrogen dioxide reacts with water. Which statement about this reaction is correct? Now, nitrogen dioxide is reacting with water. Okay, good stuff. Now he's saying, which statement is correct? Both products are formed because oxygen atoms gain electrons. Nitrogen atoms undergo a disproportionation reaction. Now, I don't want to discuss A for now, although my job is to discuss every single MCQ. I like to discuss A as well. But if I were in the exam, I'd just go over A because I probably, as a student, I might not understand what A means. But if I look at B, B says nitrogen atoms undergo disproportionation reaction. Absolutely, they do. This nitrogen is +4 here, and here it is, sir. What is nitrogen here? What is nitrogen here? -4. You can calculate it, right? Let's suppose nitrogen is X. So it's the NO2 minus I, right here. So nitrogen, I don't know how much it is. Oxygen is -2, times it by 2, add them together. Overall oxidation number is -1. X minus 4 equals -1. X equals +3, right? So that's +3 right here. And how much is nitrogen right here? It has +5. And you could calculate it like this, NO3 and H. So you could, if you want, you can calculate it NO3 minus I, right? So if this is X, this is -2, times it by 3, because you have 3 of those, add them together. Overall oxidation number is -1. X equals +5, for those who forgot this stuff. So you see, it absolutely did undergo disproportionation. It went from +4 to +3, getting reduced, and it also went from +4 to +5, getting oxidized. So disproportionation reaction is a redox reaction in which an element in a single species is both reduced and oxidized in the same reaction. So B is absolutely correct, right? And the oxidation number of hydrogen is increased. No, it's +1 on the left, it's +1 on the right. In both cases, you guys can calculate it. It hasn't increased. It's a spectator line effectively. Water acts as an oxidizing agent. No. Water acts as both an oxidizing agent and as a reducing agent, because see, in one go it's reducing it, and in the other go it's oxidizing it. So reacts at both oxidizing agent and reducing agent. If this "and" was written, then I would have selected D as well. B and D both would be correct then. But what about A, right? As a student, probably I'd ask you to not go into the detail for it when you're sitting in the exam and you've figured out the correct option for it, which is B, and without further calculations you could just have B and boom, go on. But as a teacher, it's my job to explain every single option to you. It says both products are formed because oxygen gain electrons. Now you might say, hey sir, it doesn't, but that's just, you can't make me visualize it. Why doesn't it do it? You don't have the explanation to it. You might intrinsically know that it doesn't, but you can't explain it to me. I'll explain it to you. Make the half equations for it. That's how you can easily explain it to yourself. See, NO2 is going from NO2 to HNO2 right here, and what's happening, NO2 is going from NO2 to HNO3. So can I say NO2 is going into HNO2? Now this is all extra, but again, I want you guys to do it. NO2 is going into HNO3. Can we balance these equations, please? How could you balance them? Well, first of all, balance all the atoms except for hydrogens and oxygen, 1 and 1, good stuff. Hydrogens and oxygen ke alawa, balance all the other atoms, good. Then balance out the oxygens with water, right? Now on the more deficient side, you have 2 O's here and 2 O's here, it's the same, we don't balance it out. Then balance out the hydrogens with the hydrogen ions. So you have 1 hydrogen here, let's balance it out with the hydrogen ion, and balance out the more positive side with the electron. So this is now the more positive side. It has 1 plus overall, this is 0, so I'm going to balance it with an electron right here. That's the half equation for the first one. For the second one, balance out all the atoms except hydrogens and oxygens, then balance out the oxygens on the more deficient side with H2O. So you have 2 O's here and 3 O's here. I know that I have to add 1 more H2O to balance out the O, right? And to balance out these hydrogens, 2 hydrogens, right, you have to add hydrogen ions on the more on the side where there are fewer hydrogens, right? So you have 2 hydrogens on the left and you have 1 on the right. So how many more do I need to add to balance out hydrogen? 1 hydrogen ion. Now balance out the hydrogen ions with the electrons, right? So this is effectively what you see. This is what I am seeing, right? Now look at this. What's happening? In one case, in case number 1, you can now visualize it. He's saying both products are formed because oxygen atoms gain electrons. Oxygen atoms gain electrons. In this case, you might think, hey, oxygen atoms are gaining electrons and, this is what's happening. But in this case, electrons aren't being gained. They are being lost. So in one case, electrons are being gained, and in the other case, electrons are being lost. And you could add these 2 half equations to end up with the full balanced equations. And we've done this a lot in redox. We've even covered this in redox, right? When we were writing half equations and making full equations from half equations. So please understand that not in both cases, oxygen atoms are gaining electrons. In one, it may. In the other, it's not. It's losing electrons. There's no gain of electrons right here. So that's the idea. You could have visualized it as well through these equations, but as a student, I would just recommend to circle B and move forward. This is interesting. Phosphorus reacts with concentrated sulfuric acid to produce phosphoric acid, sulfur dioxide, and water. A, B, C, D are all whole numbers. The equation can be balanced by using oxidation numbers. Obviously, it can be balanced by using oxidation numbers, you dumbo. You've given me the full equation. I can use oxidation numbers to balance it. What is the sum of A, B, C, D, E? Pretty easy. You have H2SO4 right here, sulfur is +6 here, phosphorus is 0 right here. Why is it 0? Pure elemental state. Similarly, phosphorus is what here? You guys can calculate it. Sulfur is what here? All the others are just spectators, right? So phosphorus in H3PO4, it's PO4 3 minus. You guys can calculate it. Phosphorus is X, oxygen is -2, times it by 4, add them together. Overall oxidation number is -3. X is equal to -8 goes there, +5. So phosphorus here is +5. And if you look at sulfur right here is +4. You could even calculate it in SO2. S you don't know, that's X. O is -2, times it by 2, add them together. Overall oxidation number is, oh the helly, what happened? Everything just vanished. Wait. Okay, it's back. So overall oxidation number is 0. X is equal to +4, right? That's how you could calculate it. Now, sulfur is going from +6 to +4, which means there's a gain of 2 electrons, or you could say the oxidation number decreased by 2. And here you could say, hey, sulfur went from 0 to +5, phosphorus went from 0 to +5, so oxidation number increased by 5. Now, the decrease in oxidation number must equal the increase in oxidation number, or vice versa. So what do you have to do? Make this 2 equal to 5, or make this 5 equal to 2. You basically take the LCM. 5 times 2 is 10, right? Or what you could do is you could say, hey, take this 5 multiplied with 2, take this 2 multiplied with 5, right? So multiply this with 5 and multiply this with 2. And once you multiply it with 2, 2 will drop down here and 2 will drop down here. You need to be very careful. Let's assume, and for the sake of example, I want to clarify this so much that you are never confused, right? Before I do that, let's just complete this question. So +6 to +4 into 5. So A is 5 right here, and the 5 would drop down right here. Now you just balance out the H's or the O's on either side, right? So let's talk about H's because it's easy, right? Now you have 5 times 2, you have 10 H's on the left. 10 H's on the left. You already have 6 H's on the right. Already do have 6 H's, right? 2 times 3, that's 6. How many more do I need? I need 4 more. So what should I multiply 2 with to get 4 more? X is equal to 2. So E is 2. And if you sum all of these up, 5 plus 2 plus 2 plus 5 plus 2, what does that give me? 5 plus 5 is 10, 10 plus 2 is 12, 14, 16. And therefore D is the correct option. Now please, I don't want you guys to rote learn this the way, teachers teach it. 2 is being multiplied here, 2 will drop down here, 5 is being multiplied here, 5 would drop down here, and 5 would drop down here, right? This is not how it goes. You also need to be very cautious and careful of what is written here, right? If this, for example, was P4, then what would you do? Would you still put a 2 here and put a 2 here? That's the question. That's the golden question. That's the $1 million question. And I've explained it in redox as well. Would you still put the 2 here and the 2 here? No. Then this P is just 1, right? So this 2 would drop down here, but this P was P4. So if this 2 is dropping down, it would be spoken like this. For every 2 of this, 2 of this would happen, right? But this is 4. So what do I need to do? What do I need to do with it? This 2 literally means that for every 2 of this, 2 of this should happen. For every 2 of this, 2 of this should happen. But this is 4 with me. Then what would I write here? what would I write here? I'd write a half here and 2 on the right side. Please. Now it's for every 2 of this, 2 of that is happening. This is something so crucial that every teacher skips out on, and it ends up confusing students. They can't balance equations. So please, this multiplied by 2, write it with yourself. This multiplied by 5 means for every 5 of sulfur, 5 of this would happen. And this is 1. So 5 of this, 5 of this is happening. This is 1. So 2 of this makes 2 of this. For every 2 of this, 2 of this would happen. For every 2 of this, 2 of this was happen. But what if this was 4? Then for every 2 of this, 2 of this would happen, but this is already 4. Then I put a half. And this is so crucial to understanding redox balancing through these oxidation numbers. Got it? Got it? Good stuff, right? This is so important. This concept, I think, in fact, is the most crucial concept of redox. The most crucial, and I've taught this in the live classes even. Okay, so please, if I were the examiner, I would write P4 here to purposefully get every student to incorrectly write 2 here. Which statement is correct? Aluminum chloride has a giant ionic lattice of Al3+ and chloride negative ions. Now please understand that aluminum chloride at room temperature and pressure, it's Al2Cl6, right? That's the simple molecular state for it. It's in its simple molecular state. But sir, did we not study that aluminum chloride can also be ionic? Yes, it can be, but only when it's added to water. Only then can the aluminum 3+ ion attract 6 waters to itself and form that bond with all these 6 waters, right? And so it would be the ionic bonds which would form, right? But that's not a part, right? That's not clearly given in part A, right? So I'll just say, hey, if nothing else makes sense, then I'll probably go for A, but it's wrong because at normal temperatures, it's Al2Cl6. That's the most stable version for it, right? It's a dimer of AlCl3 and AlCl3, right? Now, it says sodium chloride dissolves in water, forming hydrogen chloride and sodium hydroxide. Absolutely BS, man. Absolutely BS. Why? Because sodium chloride is namak. It just dissolves in water to give you NaCl aqueous. That's all. That's all. Nothing else. It just gives you NaCl aqueous. Right? So B is wrong. No sodium hydrogen chloride forms, no sodium hydroxide. And if you were ever confused about this, you might think, sir, but wait, sodium ion is there, chloride ion is here, and in water you have hydrogen ion and OH- ion. Why isn't this forming? This is not energetically favorable. Not energetically favorable. And you might still think to yourself, but sir, I haven't studied this, so how would I know? Think about it through basic common sense. Use your basic common sense. If hydrogen chloride were to form in water every time you dissolve namak into it, shouldn't your intestines be burnt? Because hydrogen chloride is an acidic gas, and then it dissolves to give you hydrochloric acid. So every time you put namak inside water, wouldn't it burn to give you hydrochloric acid? So even this term hydrogen chloride is incorrect, because in water it should be called hydrochloric acid then, right? So that's absolutely incorrect. And whenever you put salt inside water, do you see fumes of HCl forming? No, absolutely not. That's BS. This statement is incorrect. The strong covalent bonds of silicon chloride, SiCl4, prevent it from reacting with water. Please, this is so important. SiCl4 reacts with water. It has strong covalent bonds right here. Si and Cl, Si and these 4 Cls have these strong covalent bonds between them. But it still reacts with H2O. I've seen it. It forms an off-white precipitate of SiO2 and forms HCl. And it does so. C is incorrect. When phosphorus 5 chloride PCl5 reacts with water, the resulting solution conducts electricity, and absolutely it does. And that makes much more sense to me, because the resulting solution is ions. Phosphoric acid, it's an acid. HCl, that's also dissolves to give you hydrochloric acid, and acids do in fact conduct electricity due to free moving ions. So that's why D is correct, and I'd cross A out, because my initial gut feeling was also that A is incorrect, since aluminum chloride is the more stable form for it is Al2Cl6. It doesn't form an ionic bond, rather it forms a simple molecular structure, and the reason for that is the difference in electronegativity. It's not greater than 1.8. That is our rule of thumb. So that's the idea. Do you want me to do more or no? Bas sahi hai, kafi hai. I think kafi hai. This is enough. So till 30 MCQs we are done. We are left with 30 more for the 2024 set. This chapter, and you might see, you might even visualize it, that this chapter is so important. 60 MCQs in the 2024 papers combined, all the papers, right? So I've effectively done 6 papers. So on average, you can expect 10 MCQs from chapter number 4 in your AS chemistry exam. That's why MCQs are difficult, because this chapter number 4 is the weakest, and it's taught in such a way that students are forced to rote learn these equations, and we've actually butchered them into and dissect them to such an extent that we don't need to rote learn them. Rather, we now properly understand things. Okay, any questions, guys? Any questions?